so much for coming to our Tech Talk. It's really great to see all of you here, even though this is fall break, and I know not everyone is always on campus during this week. My name's Melanie Bhatti. I'm part of EdTech Services, and we host this series of talks throughout the semester. I'm just going to make two really quick announcements, and then we can turn it over to our presenters. So one is that you might have seen a sign-in sheet when you came into the room. We really love it when people sign in because we know how many people are here. And it's helpful for us to know if there are students or staff or faculty coming to these so that we can be in touch with you and help to tailor the topics to fit your interests. So if you wouldn't mind signing in before you take off afterwards, that would be really helpful. And then the other thing I wanted to mention is that our next Tech Talk will be November 7th. And we're focusing on some of our student interns who have been doing work with the Microsoft HoloLens, which is a mixed reality, virtual reality device. And they're going to talk about some of the apps they've been working on developing, which should be interesting sort of to anyone who's interested in imaging, in visual representations of things that are not necessarily really there, and also in thinking about how students can work on tech development like this as part of internships or courses. They have done some really cool work. So we hope that you'll join us same time, same place, November 7th. And I guess those are the only housekeeping notes that I have. And so I'm going to turn it over to our presenters, Caroline, Matt, and Sarah, to talk about photogrammetry. So follow you.
All right. Hi, everyone. Thanks for coming out to today's Tech Talk on photogrammetry, its potential uses in teaching and research. This past June, Caroline, Matt, and I, along with some of our colleagues among the faculty, staff, and graduate students here at Bryn Mawr, participated in a training workshop on photogrammetry, which was taught by Carla Schoer and Mark Mudge, who are founders at the Cultural Heritage Imaging Center, as well as their imaging director, Marlon Lum. So throughout the course of this talk, Caroline, Matt, and I are going to talk about what exactly photogrammetry entails, what we learned about CHI's approach to photogrammetry, and how it can be applied in the study and teaching of archaeology and cultural anthropology, as well as what specifically we are doing with it in our work. To begin, however, I'd like to say a few words about cultural heritage imaging, and what their mission is. So CHI is a nonprofit organization based out of San Francisco, California, that is dedicated to the development and adoption of cost-efficient and accurate imaging processes for the preservation of cultural heritage. They specialize in the development and promotion of, as well as training in various practices within the field of computational photography, including reflective transformation imaging, RTI, and photogrammetry, which we're here to talk about today. The CHI team runs trainings in cultural heritage preservation projects, both domestically and abroad. In fact, I was talking to Carla earlier this week, and they just got back from an extended project in Albania. Here you can see Carla pictured working on a photogrammetry project that is imaging Diego Rivera's Pan American Unity. The current housing for Rivera's work only allows a viewer to step 14 feet away from a mural that is 22 feet high and 74 feet wide, so not allowing people to view this work in its entirety. The photogrammetric study of this work serves to create an accessible version of this work, ensure its preservation of its content, and examine it in close detail to determine the viability for safe transport and reassemble it in a new location. CHI's photogrammetry training stands out for being software independent, although we will talk briefly about the software on which we were trained, its systematic workflow, and its emphasis on error mitigation. So what is photogrammetry? On a very basic level, photogrammetry is the use of photographic sets to render three-dimensional models. This, in and of itself, is not a very complicated process. Today, a variety of apps will allow anybody with a smartphone camera to snap away at a subject and quickly render a lifelike model. While aesthetically pleasing and certainly entertaining, however, these basic models contain little useful data about their subject. Willy-nilly photo capture and little to no optimization of the data creates abundant opportunities for error. Scientifically approached photogrammetry belongs to the field of computational photography, and its goal is to extract information from a sequence of digital images and generate new, information-rich digital representations. When used with the intention of preserving cultural heritage or facilitating research, photogrammetry becomes a precise measurement tool and archival tool for projects both large and small. Careful, geometry-driven data capture, responsible recording of metadata, and attentive processing of the data can produce models that are not only lifelike, but imbued with reliable, testable, and reproducible information on the subject. In addition to offering in-the-round views of the subjects to individuals across the world, the models produced by CHI's best practices in photogrammetry can provide measurements of the subjects that are accurate to 0.1 millimeter, while also containing quantitative estimates of what measurement uncertainty does still exist within the model. They can also be reused by others and preserved for future generations. So now on to a little bit of what the actual process of photogrammetry looks like.
Excuse me, do you think we might cut down the lights a little bit so you can see this better?
Sure. Is that better? So, good photogrammetry begins with good photography. High-quality results require photographic calibration sets with invariant focus, focal length, and aperture. Any variation in these elements requires us to calibrate the data separately, as the software uses the interaction between subject, light, and lens to calculate distance. Consequently, the setup for the photo capture of the subjects is one of the most time-consuming stages of the process, as the photographs must be well lit and as sharp and free of noise as possible. You will always want to shoot on manual mode, taping your focus ring so it's immovable, and ideally you will have even, consistent lighting conditions that allow you to set your aperture between 5.6 and 11, your shutter speed high enough to prevent blurring, and your ISO at around 100. It is best to start with a wide lens. A 24mm lens is a good, solid go-to. And later you can do runs with a longer focal length in order to increase and supplement the resolution. The wider lens can be limiting in terms of depth of field, so it's important to maintain a consistent distance from your subject whenever possible. When shooting your subject, you should include a minimum of 3 scale bars. If a scale bar is ever moved, even just a tiny bit, it has to be removed from all subsequent photos, as any attempts to match points with a scale bar will result in error if the targets are not in the exact same place. Consequently, more scale bars are recommended, 4s are preferred, although this is largely determined by the size and the shape of your subject. It's also important to shoot images with at least one set of white balance targets, as well as color cards, as we want our final models to be accurate in color as well as in shape and size. While the capture of sharp and consistent images is highly important in production of models, arguably the most crucial facet of the whole process is ensuring that you're using good geometry when deciding from where to shoot your images. Redundancy is a crucial part of all scientific measurement systems, and this holds true for photogrammetry. We want redundant images in order to ensure low uncertainty measurements. However, the nature of photography and working with lenses means that we must be more precise than simply taking as many images of the subject as possible, which many who perform photogrammetry tend to do. Oblique angles of points increase our margin of error rather than narrowing it. So, CHI recommends very specific approaches to overlap and redundancy. When shooting a complex subject in the field, for instance, you want to aim for 2/3 overlap of photographs on flat subjects, 3/4 overlap if you're working around the corners. Once you have completed an initial pass of 2/3 overlap, you want to turn the camera 90 degrees and tilt it about 15 degrees down. Make another pass and then repeat at 270 degrees, tilted 15 degrees up. These 90 and 270 degree rotations correct any imprecision that's built in with the manufacture of the lens. By changing the degrees at which the camera is capturing the image, we're characterizing how the light interacts with all parts of the lens. When all is said and done, every point should have 9 look angles. These angles provide enough redundancy to ensure low uncertainty measurements, but are also direct enough views on the subject to prevent oblique angles from increasing our margin of error. The same principles apply to the simple subjects that can be shot in the round. This method is actually preferable when it's possible to just our flat runs, as long as the camera is always angled directly at the subject matter, as this can narrow depth uncertainty. In these situations, you want to capture the subject straight on, circling it at 10-degree increments for a total of 36 photographs. Then, as with the flat runs, you want to shoot the object with the camera rotated at 90 and 270 degrees, tilted 15 degrees up and down respectively. Once you've completed the required circuits, it's important to include a flat run of the object to allow you to shoot scale and color cards. Once you've compiled your image set, the hard work is done. The best practices workflow promoted by CHI is notable in that it is designed to be software independent. The goal of good photogrammetry is that you should be able to take your data set and send it along with a good digital lab notebook to anyone across the globe, and that with the information that you've supplied them between your images and your notebook, these people should be able to produce precise, scientifically testable models. Your digital lab notebook is designed to record all contextual information that is not included in the image's EXIF data. It should tie your digital records to real-world info. A strong lab notebook would include equipment used, parties involved, duplicate records and group setup description, and location information such as GPS coordinates. It can also be used to maintain project management information, such as information regarding exhibitions or excavations, so that people who need to access this data later can understand the decisions made during the initial capture of this information, as well as how it was intended to be used. All that said, it's important to know what good optimization, or the process by which our error margins are minimized to the greatest extent possible, consists of. In our training, we worked with software called Agisoft. When using the software, we worked through a systematic workflow designed to remove error-corrupted points from our models and refine the alignment of photographs. First, we examine our data's reconstruction uncertainty, a metric that examines the geometric relationship between all of the cameras and how many photos each point is matched on to determine the potential for error in our reconstruction. We select points with a high reconstruction uncertainty and remove them from our model. Then, we look at projection accuracy, which is based on the size of the pixel neighborhood describing an interesting point. Basically, if a feature on our model requires more pixels to describe it, its likelihood for error is higher. By removing the problematic points at this stage, we ensure that our model relies only on the strongest, most well-matched points when building each feature. Finally, we examine the projection error for each of our points. We determine which points do not match well across photographs and remove the problematic matches, ensuring the precision of the matches remaining. Our goal, through iterative completion of this stage, is to eliminate all points that exceed 0.3 pixels of reprojection error. All said and done, we're left with only the best data, ensured through responsible redundancy. These points are then used to build responsible models. The Agisoft software allows us to view these models as meshes, essentially wire frames that connect each of our individual points, before hanging the visual information on each of our photographs. From each of our photographs. This allows us to see any holes or flaws in our data. While perhaps less pretty, it ensures that anyone accessing this information later is fully aware of the information's limitations and can rely on the information that is currently available. Now I'm going to hand it over to Matthew Jameson, who will talk about the research applications of photogrammetry and archaeology, as well as a project that the two of us are currently working on.
Thank you, Sarah. So exactly as Sarah was just mentioning, she's given us sort of a good basic understanding of photogrammetry and the steps involved in taking the photographs and working with the software. And so I want to get a little bit more specific now, and this might be tailored a little more towards archaeologists, but also there are points that can be taken away for a more general audience. So why do archaeologists practice photogrammetry? Why are we interested in creating these 3D models? The first reason is that we can obtain accurate renditions of archaeological sites and objects. And this is very important for a number of reasons. Oftentimes, archaeologists only have access to sites during a season, whether that's for permit reasons or for travel. And so this allows you to take your data back to the lab with you. So you can take measurements and make observations when you're away from the field. And it also removes distortion present in 2D images. So if you're taking a photograph, the lenses distort the image, and when we're using models, again, it creates an accurate representation that you can take measurements off of. Archaeologists are also interested in photogrammetry for cultural heritage reasons. So it provides an opportunity to preserve cultural heritage in an electronic format. And this is one of CHI's major initiatives. And so if we think about the Assyrian reliefs that were destroyed by ISIS, had they been recorded using photogrammetry, we would have accurate models that archaeologists could still study. Unfortunately, we do not. And we can also use it to reconstruct damaged buildings, etc. And it can also be used, and this is not just for archaeologists, but for a wider audience, to democratize information. So that people who don't have the ability to travel to different parts of the world to visit archaeological sites, if this information and these models are made available in open source formats, they can access them from their homes. And so it can increase public interest and give everybody a chance to have access to it so that we're not just keeping it for ourselves. So I want to turn now to a couple of different ways it's used specifically in archaeology. So I have these listed up here. So the first is aerial photogrammetry. So we can use photogrammetry as archaeologists to create plans, maps, and models of our sites on a larger scale. And so I have an example here from the site of Copan. And so what you see in the image here, these little red squares and squares here are where the different photographs are being taken. And so again, what's important is that you have overlap. Is this? Yeah, overlap on each of the photos. And then you can create a 3D model of a larger area of the site. So this is one example. And then here we have another of a 3D model of the Eastern Ball Court in Copan. So aerial photogrammetry allows you to create models of larger images, of larger areas. Photogrammetry can also be used on site to record things such as architecture, different contexts, or objects that are in situ. So as they're being excavated, we can create models of them. And so this is an example of a site. It's called the Ness of Brogdar in the Orkney Islands. It's a Neolithic site, and you can see the excavation taking place here. And because they're only there for part of the year, again, once they create models of their buildings, and these are actually uploaded into Sketchfab, which is an open source program that allows anybody to go and look at these. They can recreate the walls of these structures and then study them later. So this is a really important point. And finally, we also use photogrammetry to recreate objects or artifacts in the lab. And so here you can see the setup of photogrammetry being done on a Greek vase in a lab, and then this is what, it's not the same piece obviously, but what it would look like if it was uploaded into, again, Sketchfab. So those are some of the, again, sort of a basic overview of some of the uses of photogrammetry in archaeology. And now I want to turn more specifically to our project here at Bryn Mawr. And I have a little plug here. This project is part of our the graduate group symposium and an exhibition that is going on in conjunction with that. So you might have seen these posters up around campus, but there is an exhibition entitled Fragmentary Excess, Body, Text, and Receptacle that is opening on November 3rd. And there will be an online component to this as well that will include the photogrammetric models. And so that's what I want to look at right now. So Sarah and I have been working on this project, and we are including 5 objects from our own special collections. So you can see these objects here. We have a cuneiform tablet, a foundation nail with cuneiform on it, a lekythos, the head of a youth in terracotta, and a bronze jar. And so what I want to go through with you right now is our work on the bronze jar. We have finished taking photographs on most of these objects, but we haven't finished processing them yet. We're still in the process of doing that. This is what our setup looks like. So up in special collections on the 3rd floor of College Hall. Again, you can see that we have a solid background here, and that's important when you're shooting objects in the round. You don't want to have any differences in the background so that it will match up your points exactly when you come to align your photos. And you also don't want it to be a reflective surface, or else it will draw points off of the reflections. We have a turntable here that the object will be placed on. And again, you have to rotate it 36 times so that it's 10. You're getting a photograph at 10 degrees. Our lights here, the object has to be fully illuminated. And then our tripod for our camera. So it's a pretty basic setup, but it actually works quite well for what we need to accomplish. And so this is the bronze jar. So you can see here it is a fragment, so it's not complete. And so I'm going to walk you through our workflow. So this image here is the raw photo. When we're capturing images, we want to capture them in the raw. So this is the raw photo with no corrections done. You can see that it's on the turntable with our background. The next step is to pre-process the images. And so we use Adobe Camera Raw to do this. And in this step, you want to eliminate any kind of corrections that the software would want to apply to your photos. So you want to remove any of the enhancement, any color corrections, anything like that. And what we do then is apply our own camera lens, so that in Camera Raw they have a selection for each different kind of camera. And once you select it, it applies, so if there's any distortion, it can correct for that. And then, as Sarah was mentioning, we make sure that there is a color card with a grayscale in it. You can see that these photos look quite different. And so we color correct by selecting on the grayscale. And then I just wanted to show you this because it includes our scale bars as well, which will ensure an accurate model. Once we have the photos pre-processed, we save them as TIFF files that are actually uploaded into the Agisoft software. And we also save them as DNGs with the raw material embedded, just so we have all the information saved with the photographs. And at that point, it's time to upload into the software. And so we do that, and one of the first steps is to create, we call it a mask of our object. And what that theoretically allows us to do is separate out the object from anything in the background. And obviously you want to do that because you're not interested in creating a model of the background, you just want a model of your object. You can see here maybe that it's a little bit messy. And so we've had some difficulties working with this initially, and I will come back to that at the end. But I just wanted to show you what that looks like. Once we create the mask and go through the optimization process, we can start to build our dense cloud. And so I know you've seen this slide before, but I wanted to show it to you again. So here we have the dense cloud of our object. I'm sorry we can't pull up the program up here, so I can't actually rotate them around for you, which would be quite a bit of fun. But this is what the software interface looks like. So we have our dense cloud, we have our meshes, which give us exact geometry of our object. And then finally, we can overlay our meshes with, to create our 3D model with the photographs themselves, and that's what makes it look pretty. And again, just to point out, you could go through these steps and create a model that looks nice just because you're overlaying the photos, but it wouldn't be as accurate as this workflow process is. And then the last step for us, for part of the exhibition, is to output our model into Sketchfab, and you can see what it would look like here. Again, it's not as nice as we're hoping. We still have to clean it up a little bit. And then eventually will be uploaded to our online exhibition. So that's all great. But I want to talk a little bit about some of the preliminary issues. And so because we're working with fragments of ancient objects that don't necessarily stand up on their own, we have to give them support. So we ended up putting the bronze jar in silica beads, which we weren't thinking clearly, are also green, so that when it came time to make the mask, it thought that the silica beads were part of our object. And that's not necessarily a problem. We can go back and correct that. It just means a lot of extra work for us. And the other issue is working with Sketchfab. When we output the model to a PDF, it looks pretty nice. It looks great. We don't see these sort of blemishes that we're seeing in Sketchfab. And so we're still trying to work through this software. But I also just want to point out that we are compiling a Google Doc that will be available up in special collections for anyone who wants to work through our process. And hopefully, by the time it's finalized, we'll have ironed out all of the errors. So that's our project. And now I want to hand it over to Caroline.
All right, so I'm Caroline VanSickle. I'm a professor in anthropology, and I am a paleoanthropologist by training. Hold on, let me. So as a paleoanthropologist, I study human evolution. So my days are spent looking at bones of these kinds of creatures, basically, which we call hominids. And that means that a lot of what I do is comparing shapes of bones to the shapes of other bones of other species. And so I'm just going to spend the rest of the time here, try and keep an eye on the clock and everything, talking about how I see photogrammetry fitting into a workflow in paleoanthropology in particular. Keeping in mind, I just learned how to do this technique in June. I have not actually done any of this myself yet, but I have some colleagues who are working on this as well, and I think there's places to go with this. So, without further ado, paleoanthropologists can use photogrammetry to take measurements from home. Matt mentioned this, just as when you're working as an archaeologist and you have to spend only part of your time in the field and then you come home and you're like, oh, I wish I had measured something. The same thing is true for paleoanthropology. The fossils that I study are often housed in museums and sometimes under giant glass cases like this, and so they are not readily available. In the past, the way that paleoanthropologists have gotten around this, there's two methods. One, you are able to go and visit the collection at whatever museum in whatever country you need to go to be able to look at the particular fossils. And this usually requires going outside the United States because we don't really find hominids here. And that is, of course, time-consuming and costly and all of that. And so it's only something that's available to a certain few who are able to get grant funding for that. Or you are able to measure casts, and casts have been made by taking the fossil, so some fragmentary piece of bone, making a mold out of it by putting it into some sort of like gel or something like that, pulling the fossil out, praying that you didn't actually break the original fossil in the process of making the mold, using that mold to make a cast that can vary in quality in terms of what it's made out of. Every time you make another cast from that mold, the quality decreases, it decreases, it decreases. And so depending what level of cast you receive, you are not necessarily getting the most accurate results if you're taking measurements on these bones. To add to this, these casts are really quite expensive, and so they are still only available to people who have the funding to back them up. Photogrammetry makes it so that, of course, you can, if you're able to go and see these fossils, or if anyone in the field is able to go and see these fossils, they can take pictures of it. They can upload a stack of photos to Sketchfab so that you can do your own processing to make a 3D model, or they can upload the 3D model itself and you can use that. And then you can open, I actually do think this is Agisoft. Yeah, Agisoft Photoscan, or a number of other programs, including some that are open source, and basically take measurements on these 3D models themselves without having to, fund the travel to go and see them in the first place. So taking measurements from home is a pretty big deal. It's going to change how many researchers are able to do this. It's going to make it so that it's not just the old researchers who have been doing this forever and have data on fossils who can write about it. It's going to make it so that new early career researchers are able to do this even before they're able to get like the big NSF grant to fund a world trip of all of the fossils and things like that. We also are able to not just take two-dimensional measurements, like the one in red here. Just to be clear, this is not a hominid. I found this picture online. This is a hominid. This is a human, actually. And so one of the things we're able to do is there's been a lot of work on how to basically use statistics to compare 3D geometric shapes, and this is called geometric morphometrics. And the concept is basically that you have an object, like a bone, or a skull in this case, and you place dots or landmarks along in locations that you are able to say are homologous between one individual and another. So there's a line on a skull that goes between, like right at the bridge of your nose, right where my glasses are basically, going like this, that is a very clear spot where two sutures cross, and so you're able to identify this in multiple species, and so you can put a dot there, like this one here. What is neat about this technique is that you can identify a couple of like solid dots, and then you can tell the software basically between these like two landmarks that I've just placed, there's a curve. And on that curve, I want to place 100 semi-landmarks. And so it'll just like evenly space 100 dots in between those first two dots that you identified. And this way you're getting the shape of the curve, not just the shape of those two dots initially. And that's something that's actually a pretty big deal, because back in the olden days when we had not so great of techniques for doing this kind of stuff, we were really limited in how we're able to compare shape differences, complex shape differences in the skeleton. And so we were limited to these like two-dimensional linear measurements, or coming up with some like weird contraption that you have in your lab and nobody else has because you built it yourself in order to do this. And so this makes it something that we can do kind of across the board. So what you can do with this is you can plug it into a program that will basically help you identify differences. So here we have skulls from a bunch of different species of primates. So humans over here with the orange dots, we've got baboons, chimpanzees, some monkeys. And what it does is it basically will produce an analysis like this that will tell you kind of where things are different. And depending what you put into the analysis, maybe you're looking at species differences, like what's being shown here. Maybe everything you put into the analysis is the same species, but it's showing you sex differences in terms of what those shapes are, or something like that, or population differences, or changes over time. And so it's up to the scientists to interpret these results, but it can be a useful visualization method for what to do with the 3D model once you have it. We can also actually print these 3D models. So this is I believe it's a Xertrax 3D printer in action. It's in the process of printing out a skull. So this is like the bottom of the skull here. It'll be facing upwards. It has these kind of plasticky things that hold it in place as it's doing this. But you can take a 3D model that you created through photogrammetry, and you can literally print it out with a 3D printer, which means that then you have something that looks like a cast, but it's plastic and much cheaper to reproduce, that you can use in classes to teach, so that you can rapidly increase the amount of materials that we have in our intro anthropology classes to show students to say, hey, this is what the hominid fossil record looks like. And so that's something that in both of these cases, I believe they were done not based on photogrammetry, but it's something that photogrammetry creates the same kinds of 3D models that could be used for this. You can also, and I'll admit, I don't know a ton about this, but I have one colleague who is using these kinds of techniques to interact with fossils in 3D. And so he actually did do photogrammetry on the hanging skeleton here, but he's working with his school to, and I should do a shout out to him, his name is Adam VanSickle, he works at Wellesley, and they are putting together what looks to be an awesome program where basically you can load in fossils or bones of different species and interact with them in a virtual reality environment, comparing them and having them kind of float around as you are looking at different features and things like that. And so he's already in the process of developing this and having his students test it out. So this is from earlier this semester. And so that's something that I'll admit, I don't know how to do anything having to do with VR. I should come to the next talk on this. But it's an interesting place to go in terms of what we can do with this technology. We can also use this just generally to reconstruct past events. So these are the Laetoli footprints, which are rather famous footprints from hominins that were left behind. And I'm just going to go through this kind of quick because it kind of repeats something that Matt said, but basically it's this idea that when you excavate something, there is a level of you're destroying the evidence as you're removing it, especially if that something is an impression in the ground like a footprint. Now these have not been destroyed, thankfully, but it's something that in the field, we could certainly take pictures of these, and if we have the scale bars next to them, they would be pictures that we could build a 3D model of, measure, and have preserved even beyond, if anything were to happen to this site. Or if there was something underneath this that we wanted to excavate, which meant that we had to destroy these in order to get to it, that kind of thing. So it makes it so that we can kind of reconstruct what's happening in the past and save that information for the future. So I have some, I made it sound like paleoanthropologists are all about photogrammetry. We're using it all over the place. We're not yet, from what I can tell. We're using laser scanners. And photogrammetry is useful because it allows us to make a 3D model that is reproducible, has low error, and is very precise in its measurements. The next engine laser scanner, which most of my friends in anthropology, that's the scanner they have in their lab, that's the one that we have in our lab here, does not allow us to do this. It does create scans. They vary in their resolution. There might have some error in what's going on, but a lot of the processing that we do in the GSAS software actually happens in the machine itself. So that's already happened when it spits it out and gets it onto your computer, so you're not able to really reconstruct what kind of error was there, what was happening, how is it doing these measurements, in the same way that you can with photogrammetry, where you have these scale bars where you identified the points that it was going to measure and told it to ignore these points because they were taken at an oblique angle, that kind of thing. So I like photogrammetry as something that could be used on fossils and bones in general because it is easy to share the photos. The photos are the raw data. It makes it very easy to reproduce anything that's been happening. And it's a lot more affordable than some of the scanners that are out there. So I mentioned the next engine laser scanner. That one's pretty affordable, but it's also questionable quality in terms of the results. There are structured light scanners that do a much better job at this kind of stuff. However, they are in the $15,000 and up range for prices, which means that if your lab has one, you're not really going to want to hand it to a student and say, here, go scan things, because that's like a lot of, well, to me, that seems like a lot of money. Again, haven't got my big NSF grant yet. So that's kind of, to go back to Matt's point about democratizing this kind of thing, when the equipment that's being used is a digital camera, and mind you, it is a nice digital camera, you might be able to have multiple cameras in your lab, and you can train students to use these and maybe actually have this be something that you can work into a classroom activity or an honors thesis, that kind of thing. And so it's something that is a little more accessible in terms of being able to actually do this so that you can get these 3D models that then you can do so much with once you have them. I don't have anything else to do. All right. Thank you.
Are there any
Questions?
questions?
Yeah.
Yeah.
I actually have a question for you two. So when you guys were photographing the the jar, why did you take it off of its stand? Was there a reason for that?
So for the purpose, and we're rethinking this decision now.
Yeah.
For-
Yes.
Moving
Yeah.
forward.
Yeah.
For the purpose of what we wanted to do with the models is we wanted every element of the object to be accessible and visible. And this stand,
On the back,
it blocks information, right? When we go to shoot the head, which is one of the few things that we have not shot yet, we're thinking about leaving it on the stand. There's also a couple other ways we've thought about maybe dealing with the issue with the glass beads. One of the other problems with the glass beads is also not just that they're green, it's that the bowl that they're in is moving, right? So the background doesn't move at all as the object is moving, which is the goal. The mask deals with what's not moving. But that bowl, that jar, or whatever, and the beads themselves, because even though they are fairly uniform or slightly different, when those are moving, it becomes difficult. So one of the things we thought is we can also put like a thin black cloth between the beads and the object. But the first and foremost, object safety. These are precious fragments. So we might be leaving the stands on in the future, but it really does. That's going to block. That information won't be accessible in the model.
Especially on. Sorry.
Is that part broken?
Yes.
Yeah, and especially on the bronze jar, the stand that it had really did cover up quite a significant portion of the back, and you can really see some of the corrosion. And again, even though we had to do a lot of work to clean it up, in Sketchfab and in our PDF output, you can really see the detail on the metal really nicely, and that's something that you would lose if you had the stand. So it's a give and take. I mean, definitely covering it with some sort of like the beads or some sort of black cloth, or using a like a vessel that's more circular. So because again, it's getting different angles on it there.
But even we had one situation. The nail that we shot was in more of a properly circular bowl. But the beads themselves are still probably going to be slightly problematic because as they're moving, they're reflecting the light slightly differently. It'll be easier to deal with than with this jar. But it's all a negotiation. That's one of the reasons I said that actually setting up for taking the photographs is one of the most time-consuming processes.
Yep.
I mean, yes, we're leaving some of the software running overnight because as it's doing its thing, it can take 24 hours, but you can walk away from that. But negotiating object safety and how to shoot these things is really the tough part. Then once you've got that set up, you can shoot them, you can upload them, you can let the software do its job. But this is really the tough decisions, and we've spent a lot longer in the lab than we expected to trying to negotiate some of these.
Well, the stand that the head's on is just, you won't
It's
see it from the
minimal.
outside.
Right.
You don't see it at all.
Right,
It's just
'cause
sitting, the head is just on top of it.
Right, and so in an ideal world, we wouldn't even have that because we would take images of the head flipped, so you can actually see into the hollowness of the head to truly get as much information as humanly possible. But we're really.
Could you still do that? Could you have it rotate on the stand and then remove it from the stand and take pictures of it upside down?
Do like the flat run? Yeah. So that's one of the options we're looking into.
I'd be interested to see how that works.
Yeah, and so also figuring out what to do flat runs of to increase the information we're gathering and that sort of thing. Yeah, there's a lot of decisions that go into.
There's always you can always take more photos.
Right, and that's something that Caroline had on her last slide about about the fact that one of the really nice things about photogrammetry is that you can always add more photographs. They don't have to be taken at the same time. They don't have to be taken by the same people.
Yeah.
As long as the person who's putting together the model recognizes that these photos were done at a separate time by a different camera through good digital lab notebook recording, then they know to calibrate these images as their own sets, they can be added 5 years, 10 years down the line. Right, in order to make
some good longevity on how this technique can be used. So I actually have an example of this, which I realize is why I put the footprint slide up. I just couldn't remember it at the time. It's a little intimidating up here. Is that I have a friend who, there was basically a line of footprints similar to the Laetoli ones, not the Laetoli ones, but they found them in like the 1960s. They took pictures of them, like 3 or 4 photos maybe, and then they excavated underneath it because there was more stuff to be found. They wanted to try to get to the bones. And then they discovered the Laetoli footprints and like, oh, these are a much bigger deal, and so we're gonna focus on those. And so these other footprints that were found first are basically forgotten. And my friend has kind of like dug these up and actually contacted the photographer to get these photos. And keeping in mind that there is no scale, and so this is the kind of like with yourself when you can take pictures of anything and create a 3D model version of photogrammetry. But they were able to actually use photogrammetry to create a 3D structure or a 3D model of these footprints that don't exist anymore, that were done on like not digital, but just an SLR camera from like the 1960s. And they were still able to actually get some information out of this, mainly because he cared more about the shape than the size of things. If he wanted the size, he would have been in trouble. But it shows that here, you know, God, that was like 50 years ago, and here we're able to actually look at the materials there. So there's always this promise of being able to add more.
Yeah, I just want to say two things about the scale bars really quickly. So again, one of the nice things about just taking more photos is if you take one set of photos with your object with scale bars, the photos that you add, you don't need to include your scale bars because it will make that correction for you.
Yeah.
Another thing is even though we use these scale bars because we're doing following CHI's process, you can also, if you have a total station or something like that, I know this is something that I've talked about with some of the other grad students, but if you mark the spot in your photographs with say an X and then shoot it in using a total station so you have that exact location, you can also enter that into the software and create your own scale bars. So that's another option.
And to touch on Matt's first point there, it's actually better if you don't reshoot the scale bars because not all scale bars are created equal. So for everything that we're doing, the collections bought a set of scale bars from CHI. They sell their own versions that are very, very, very precise. When I say that we're able to get our models down to 0.1 millimeter, it's because our scale bars are really excellently calibrated. So if you have a set of scale bars in one calibration of your photos, don't put new scale bars in.
Yeah.
It's going to end up, unless they're created by the same manufacturer and you can guarantee the same level of precision across them, you want to stick with one set. And that's actually better to take them in one set and then remove them because the moment you touch them and move them, it can throw off all of your measurements. So less is more in those.
In the example of like an archaeological site, if you scan like this part of the wall and you have scale bars in it, and then you go back the next season, you're like, actually, we want to scan this next part. As long as it's connected, you can just keep adding to that.
As long as you ensure your overlap with the original
just make
set,
sure it's overlapped.
you'll never need to add the scale bars again. Yeah,
So you could technically,
cover more.
yeah, you could do an entire site just by having your scale bars in one location, as long as you ensured 2/3 overlap on all of your photos as you were moving around the site.
Any other
Any other
questions?
questions?
The aerial photogrammetry,
Mhm.
I'm assuming this is happening with like drones or
Yes.
balloons or something,
Yeah.
and how can they sort of do like precision, or how do they ensure that there's like the overlap and
The 2/3 overlap, yeah. I mean, most that are done with drones, at least, you will have like a viewpoint of your camera, so that if you can then divide your screen into grids, and then you're flying your drone, you can do it visually.
Remote capture is your friend.
Yeah, if you don't have that,
yeah?
I think then, at least my sort of basic idea would be to just take as many photos as you want, and then you can go back through and before processing them, take out the ones that give you too much overlap. So that, yeah, I mean, that's how I would do it. Again, every time I've been on a site and we've used a drone, we do have, like a handheld that shows us exactly what we're seeing.
Something that's also to be said for muscle memory, I mean, something that we've definitely noticed doing this, is that you get a good feel by the time you've done your first pass of 2/3 overlap of how large of a step you need to take between each of them, because that's not going to change, right? And so I would imagine when you're doing aerial photogrammetry, I say having never done it, if you can do a single pass and get a feel for the timing between each of them for the 2/3 overlap, bring it back down, make sure that it looks right, that you're getting the overlap that you want, and then you can wing it, eyeball it
You
to a
probably
degree,
could,
and
yeah.
get enough, right? Take maybe more than you need to, but you'll have a good feel for what's necessary as you go and what the timing should look like as you're capturing. Any other questions? Yeah.
One question. The Google Doc, is it in
Oh, yeah.
your lab notebook or is it like a tutorial?
So this was designed, Marion Weldon wanted to put something together to allow anybody to learn how to at least do the process. If not, maybe understand all of the decisions that go through it so that an undergrad working in collections could work through step by step.
We've gone through and
create
done a
models.
very precise, everything you have to do with the camera, everything you have to do to determine your exposure, your setup, your subject setup, all of the software stuff. We include screenshots of the software so that, there's always going to be little things that might come up, but at least this gives you a pretty accurate, really step by step.
And you could see maybe somewhere up in the margins where we have this open while we're working with it and going, this doesn't actually work, and making comments to each other. So we're hoping through the course of the project, maybe by the time we get the exhibition going, maybe not, enough of us will have worked with this and kind of finagled will have enough eyes on it that it'll be pretty foolproof.
So there's stuff like this.
Yeah, so come back and rewrite this stuff because our masks have not been foolproof yet. But yeah, so it's kind of a working document that anybody who's interested in at least learning the step-by-step process of photogrammetry can go and play with. Tell us what works and what doesn't work, please. And then obviously if anybody's interested in more training on why these decisions are important or what the errors actually mean and stuff, that's something that's not included here, but that any of us are happy to talk about as well. But this is geared towards any undergrad or someone who just wants to make a 3D model for anything, and the whys aren't important.
We should talk about Creative Commons licensing. It's a way. Yeah. Making it available.
We should include Marianne on that too.
Yeah. She's been the driving force between the Google Doc. She yells at us every time we're up there to make sure we have this open while we're working, so it gets edited as we go.
Yeah.
All right.
Thanks for coming.
Yeah, thank you.
Everybody.